Hi, I'm Joe Munchak. I'm the Vice President of Mission Science here at Tomorrow.io, and I lead our Mission Science team, which is a group that's tasked with producing the data products from our satellites and ensuring that these products meet the highest possible accuracy and lowest possible latency. So today I'm going to be talking about the Tomorrow.io microwave sounder constellation, the mission as a whole, and where it fits into the ecosystem of other satellite missions that operate at similar wavelengths. So I'm going to spend a little bit of time first talking about the technical specifications of the Tomorrow.io microwave sounder payload. Then I'll talk a bit about our constellation as a whole and the coverage that it offers and how that's enabled by the different orbits that we fly in. We'll dig into some details about how the instruments have been performing now, in some cases with over a year and a half of data from space. And then I'll do a deep dive into the data products that we offer from these satellites. So first, what is TMS? It's a 6U CubeSat microwave sounder, and you can see an image of it here in the middle. It has heritage from a NASA-funded science mission called TROPICS. That was the first CubeSat microwave sounder that was intended for a rapid revisit of tropical cyclones. So that was in a 3U, which is about the size of a shoebox. TMS has doubled that size, which has given us some space to put on additional calibration targets, as well as improve some of the electronics in the receivers to get a more stable and accurate temperature measurements in particular. So it's an advancement of this already high-tech NASA design, and we've launched 11 of them to date and continue to build more as we prepare for the future Constellation launches. So at this point, some of you may be curious what exactly a microwave sounder measures and how it differs from conventional weather satellites. So you can see here the electromagnetic spectrum ranges from radio waves all the way to ultraviolet. And weather satellites conventionally measure in the visible and infrared portion of this. So here's an example of a GOES visible satellite image over the United States and the Atlantic Ocean and South America. And this is where we typically see the cloud patterns and surface and dust and haze also shows up in some channels. The geostationary satellites also offer water vapor channels that use infrared wavelengths. And so what you see here now are water vapor patterns at mid levels of the atmosphere, as well as the same cloud patterns that we saw in the visible image. Finally, the traditional imagery uses what are called window channels in the infrared. These are slightly longer wavelengths that aren't sensitive to water vapor, but allow us to see down to the surface temperature if the sky is clear. But if there are clouds, all that you are really seeing here is the cloud top temperature. And so the bright colors here indicate clouds, and the darker colors are the warm surface. So when you go to the microwave, that's quite a big step in frequency now. We're talking about a factor of 100 or more in wavelength increase. So now what's happening is that the wavelengths are much too large to interact with the small cloud particles. So instead, we're seeing through the clouds and we're seeing other features. Microwaves are also sensitive to water vapor, but this is now water vapor without that cloud impact that like we saw with the geostationary imagery. And so now we're seeing the water vapor patterns underneath those clouds, and we're seeing the precipitation cores within the convection. Those are those bright colors that you see here. And finally, we also have window channels in the microwave. Those see down to the surface. There's much more land-ocean contrast in these, so we can see that land-ocean boundary distinctly. We can see water vapor patterns over the ocean with this quite clearly, and we can also see that precipitation signature. And this doesn't even showcase the temperature profiling capabilities that these channels have as well. But TMS has 12 different channels that were specifically designed to measure temperature and humidity at various levels of the atmosphere, as well as see through to the surface in those window channels. So we can sense surface temperature as well as the cloud and precipitation properties throughout the depth of the cloud, not just the cloud top. The TMS constellation, as I mentioned before, consists of 11 satellites that have been launched to date. These have been launched into 6 different orbital planes that provide us round-the-clock coverage. You can see here, this is an animation composed of 3-hourly snapshots, and you can see that we have these distinct clusters of data. Those are the different orbital planes that we fly in. When you take all this data and count how many individual passes a TMS satellite has over any given location and do that, average that by latitude, that's what I'm showing here on the right. That's our zonal mean revisit rate. And you can see It's about 1 hour on average. So we have a 1 hourly average revisit rate. And then in some places, it's a little bit worse. In some places, it's a little bit better. It depends on the nature of the orbits and how many overlaps we have. So right around 45 degrees, we have some orbits that are in that inclination. So there's a little bit more frequent coverage there. And again, right near the poles as well. With our polar orbiting satellites, we have better coverage there. But overall, it's about 1 hour average revisit rate. And this happens at certain times of day because of the orbits that we launched into are what are called sun-synchronous orbits. So those ones, satellites always pass over at the same times of day. Those are the straight lines on these plots, and they happen around 11 a.m., 11 p.m., and about 5:30 p.m. and a.m. At any given location. We also have those 45-degree orbits that those ones change the time of day that the satellite passes over a given location on about a 60-day repeat cycle. So the combination of these offers the hourly average revisit with minimal gaps in between passes. And finally, we didn't design TMS to operate in a vacuum or as a standalone mission. It's designed to complement government-operated backbone sensors with rapid revisit. And so if you were using just a government agency-operated satellites, such as the ATMS instruments on NOAA satellites or the European Meteorological Satellite Agency's MEDOP series, along with some research missions from NASA and JAXA, you would get the coverage you see on the top panel. On a 1 hourly basis, there's large gaps. The satellites tend to occupy those same few specific planes by the operational missions, and other times of day don't have very much coverage. But when you add TMS to the mix, now we're covering the vast majority of the globe, even in a 1 hourly time frame. And the most recent data at any given point most likely comes from one of the TMS satellites. So it's great that we have this coverage that is on par with the ones operated by government agencies. But how did the instruments perform? After all, a poorly performing instrument will not provide as valuable data. So we have taken great care to, first of all, perform accurate calibrations as well as validate our data against many different independent sources. So for a microwave sounder or any microwave radiometer, there's an intrinsic measurement of the instrument's noise. That's called the noise equivalent delta temperature, or NEDT. And this is just the basically pixel to pixel noise level that we observe in that instrument, how much variation there is if they were looking at a purely uniform scene. Then for the validation, we see how well the measurement is comparing to what we would simulate from that other validation source. So we have, if we wanted a validation everywhere, we would use a model reanalysis. So this is a model's estimate of the state of the atmosphere that we can simulate our measurements from. And that model is not going to be perfect because it doesn't have measurements. It's not assimilating TMS data. So it's relying on numerical weather prediction to propagate the state of the atmosphere properly. And so there is going to be some error. It's never going to be a perfect match. In particular, it doesn't handle clouds very well. So we do screen out clouds from these analyses. And depending on the channel, some channels we're getting very close to the NEDT. Other channels that are more sensitive to clouds and water vapor don't do quite as well. So that's what you see in the orange bars there. But another thing we can do is validate against other satellites directly when our satellites pass over a location at the same time as these other satellites. So we picked two satellites that are known in the community to be very well calibrated. Those are the ATMS instrument aboard the NOAA polar orbiters and the GMI instrument on NASA's GPM mission. And these have a handful of direct equivalent channels to TMS that we can compare directly. And what we see here is that the TMS measurements are closer to the other satellites than they are to the reanalysis, which tells us that we're observing a state of the atmosphere that has information that the reanalysis doesn't have. So we should be able to improve forecasts. Finally, we also use radio occultation profiles, which are very good at measuring temperatures in the upper troposphere and stratosphere. And we also find there that we see similar or better performance of TMS compared to those instruments when we compare it to ERA5. So on the whole, we're seeing that the data quality is good. In many cases, it approaches the noise level, and even in channels where the scenes are very complex and have a lot of clouds and water vapor features that aren't well represented in the models, we still measure other satellite or compare to other satellites better than we do the reanalysis. We also look for things like biases with respect to latitude. Those tend to be very small, as you can see in this image from some of our newly launched satellite, TMS-10. And also across the dynamic range from cold scenes to warm scenes, we don't see any trends there. We mostly line up right along that one-to-one line when we compare to ATMS and the channels that we have in common. There's a lot more detail on this in this publication that's now currently in a revision and review stage, but a preprint's available online at this link. We've also had some independent validation. This particular comparison comes from Professor Mitch Goldberg at CCNY, and he took an approach where he took our data and matched it up to the ERA5 reanalysis and then attempted to retrieve the state of the atmosphere on an independent time period just based on the information that was present in the TMS channels, noise and all. And he did this not just for TMS, but also for ATMS and the Arctic Weather Satellite, or AWS, which is the prototype satellite for the EPS Sterna constellation, which is another microwave sounder constellation that won't come online until the 2030s. And what he found was that, first of all, ATMS is the best performing of the three. We see the lowest error there. But ATMS, of course, has many more channels and lower noise per channel, so this is not expected. It's a much larger class of instrument. What he also found was that TMS compares favorably to AWS, both in temperature and humidity, or at least equivalently, despite being a much smaller form factor. And again, TMS has a constellation out there now, whereas AWS and EPS Sterna won't be around for another 4 or 5 years. So if you're interested in our data products, we have a whole suite of level 1 and 2 data that contains the brightness temperatures. It's all processed through Argo Workflows, which is a data pipeline system that operates on Kubernetes clusters through various cloud compute providers. And it's automated every time we get a downlink from the satellite. We produce these products and deliver them usually within 10 minutes of receipt of the L0 data. So I'll walk you through our level 1 products here. Our fundamental or lowest level of level 1 product is 1BTB that contains the antenna and brightness temperatures at the native sensor sampling and geolocations. So you can see there a typical scan pattern. The antenna temperatures are combined into a brightness temperature after some antenna pattern corrections are performed. We also have a 1BTBR product, which is where all the channels are resampled to a common geolocation. This can be useful for applications that require each channel be at the exact same center location. And finally, we have a 1CTC product, which is the same sampling as 1BTBR, but now we are converting everything to a common spectral response. So all the different TMS instruments look identical after they've gone through this intercalibration process. We also have a 1CTCR, which is a spatially resampled 1CTC. And you can see here the difference. The native sampling, even with the 1BTBR, has the typical scan pattern that you see from a cross-track scanner, where the footprint spacing is wider apart at the scan edges than it is at the center of the scan. And so what we've done with TCR is resample so that all of the pixels are equally spaced apart on the surface. And this is particularly useful for image-based machine learning applications such as UNets. We also have a field in this product that performs what's called a limb adjustment, which is where we remove the scan angle dependence of the brightness temperatures by applying a neural network limb adjustment algorithm. You can see here what's been done with this image is that this channel is always colder on the edges than it is near the center of the scan, because the edges are seen higher in the atmosphere where it's colder. This is a temperature sounding channel, and so we've managed to mix the channels in such a way that you're looking at a uniform height response. And so you see uniform temperatures across the scene, and any variations that are there are due to actual changes in the temperature of the atmosphere, not just changes in the scan angle. We also produce level 2 products. These are intended to get back the state of the atmosphere from the measurements. And so we're retrieving temperature profiles and humidity profiles, as well as a few integrated cloud parameters such as ice water path, liquid water path, precipitation rate, and storm top height. And these products are also available. And again, we've validated them, and they compare very similarly to products from other microwave sounders, such as the MIRS product from ATMS. Finally, some users may be interested in gridded data that's on a uniform latitude-longitude grid. So we have started producing a level 3 gridded ZAR product. ZAR is a cloud-native data format that allows for ease of access and subsetting along any of the dimensions of the array. So in this case, the dimensions are time, latitude, longitude, channel, and satellite. So You can sample the entire TMS data record by querying against this. And here's some example applications looking at one satellite at multiple times throughout a day, or multiple satellites within the same hour, or even performing very short-term time differences of brightness temperatures to look at convective growth and decay, which is something that can only be done with a constellation like TMS. So thanks for your time. I hope that this has whetted your appetite for interest in the TMS data. I believe the next speaker in this webinar will be Ryan Honeyegger, who's going to dive into more of the applications of TMS. Thank you.